Hi, please do this problem. I knew you could do it. Great job. Now we're going to watch a brief video. Wow, what an informative physics video. What happened in that video? Daisy? The coyote couldn't run fast enough to catch the roadrunner. So he squished a spring, and then the spring launched him toward the roadrunner. Good, that was fine. But now let's explain it in work terms. Daisy. The coyote couldn't do enough work on his body to give himself enough kinetic energy to catch the roadrunner, because, as we all know, work is change in kinetic energy. So instead, he did work on the spring, and then the spring did work on him, launching him toward the roadrunner. Wow, really good. Anything else happen, Sage? Yeah, the rock fell and squished him. It was very funny. Ha ha ha. Yeah, but in physics terms, right, Sage? Oh yeah. The rock was way up in the air, moving kind of slow. Then gravity did a lot of work on the rock and gave it a lot of kinetic energy. Because again, as even I know, and I'm a baby, work causes change in energy. So gravity's work gave the rock kinetic energy to squish the roadrunner, to squish the coyote by moving really fast. Good job, babies. And guys, if my babies can do it, you can do it too. So, look at this. Roadrunner is kind of like coyote is kind of like has like a long face and then like this way like perfect. It's not like an evil demon. It's a coyote. He's squishing the spring. He's doing work. The coyote does work on the spring. He applies force F. It gets displaced distance D. Great. Hooke's law is F equals KD, or negative KD. But it's also very commonly written as X, Kx. And we're going to use that today because I said so. So coyote squishes the spring with force F, it gets compressed distance X. Great. He did work. So he did work on the spring before the roadrunner passed him. Then, when the roadrunner passed him, he let go of the spring, and instead of him doing work on the spring did work on him. not an ant with like a long proboscis. It's a road rat. It's a coyote. And then he always like his feet are like a circle when he's running. So when he lets go, the spring is doing work on him, pushing him forward with force F over distance or displacement D. Again, work is FD. You guys are gonna have your minds blown. It was the same amount of work. The work he did compressing the spring is the same as the work the spring did pushing him. How can we describe the action of compressing a spring and hanging on to the energy to use later? What can we describe the energy that the spring has as? If you get it right, cool. If not, it's fine. It's called potential energy. And the symbol is capital U. Sorry, it is. The coyote squishes the spring doing work, and there's a lot of energy used up. Remember how we always used to say, oh, a rock's flying through space. If you do work on it, it'll speed up. If you do negative work, it'll slow down. The coyote is doing work on the spring. Did the spring speed up? No. When the spring's compressed, it didn't speed up. It doesn't have kinetic energy. It has potential energy. And the thing about potential energy is you can get it back. When the coyote lets go of the spring, the potential energy turns back into work. The spring does work on the coyote, and it gives the energy to the coyote. So instead of, so again, what happens when you push a rock in space, Hazel? It speeds up. You do work, it gets K kinetic energy. Yes, good. What happened in this scenario? The coyote did work on the spring, but it didn't speed up. Yes, good. Then what happened? I don't know. Daisy? Then after that, the spring did work on the coyote, and the coyote sped up. Yes. So it's the same as we described. Doing work gives something kinetic energy, but there was a little step in between where the spring had not kinetic, potential energy. It's all that. Potential energy. Yes, great job. Okay, so U is potential energy. There's only two kinds. US for springs and UG for gravity. In real life, there's lots of times when you can do work. Like I can push my marker across my hands and it didn't speed up. That's true, but it's not relevant. We only care about when you push something against a spring or when you push something against gravity. And we're going to look at that first. Let's say instead of the rock falling, the coyote just lift the rock, or I just lift the rock. I'm very strong, and I grab a rock of mass M, and I lift it up to a height h. The work, how can we find the work done? Yeah, how do we find the work I do? If I lift it from the ground up to height h. If I lift a rock of mass m, height h, how much work did I do? Well, the force needed is not m. It's Fg. Mg. And the work is Fd. F is mg. D is h. Okay, so I did work on the rock. Did the rock gain speed? I didn't really say, but let's pretend I said no. Pretend I lift it really slowly, So it's going very, very slow the whole time, and it's not going faster at the end. It's going the same speed, approximately 0, at the bottom and at the top. So the rock didn't gain speed. It didn't gain kinetic energy. This work must be a change in energy. So if it's not kinetic, it must be potential, UG. UG. UG equals mgh. I'll come back to this later. Same thing for the spring, right? Let's find out. Erase it. If the coyote compresses the spring distance x with force F, then work is Fd. Well, the force is Kx, and the distance is x. So would it be Kxx? Kx squared? It might be right. You tell me. Did I make a mistake? If a coyote compresses a spring, distance x, and the spring constant is k, is the potential energy of the spring Kx squared? I did make a mistake, but it might take like a, not a big, like a medium brain. Not like a 4 head, maybe like a 5, maybe like a 4.5 head to figure this out. Nothing like an 8 head like you guys have. It does take force F to compress the spring all the way. Yeah. The coyote in the video, he had to push really hard. He's like, oh, I bet this roadrunner better be real delicious because I'm doing a lot of work. He pushed really hard to compress the spring. But does it take that much force the whole time? How does the force needed to compress a spring change as you compress it more and more? Oh, I heard you say it. Great job. Yeah, good job. The force needed to compress the spring increases. Remember, force is Kx. The more you compress it, x, the more force is needed, F. So the force needed is not always Kx. I'm coming back to this. Oh, let's draw a graph. The force F to compress a spring distance x is not constant. This is wrong. It starts at 0 and increases linearly. F equals Kx. It takes 0 newtons at first. The more you push, the more you compress, the more force you need. So yeah, this max force is Kx. But the minimum force, the beginning force, the lowest force, to compress a spring 0 meters takes 0 newtons. So like 0.00001 meter, so like 0.0001, like a very small distance would require a very small force. What do we do? If we were in calculus, we would take an integral. But for us, we're taking the average. F min is 0, F max is Kx. So it's not this. It's F avg times d. F avg is Kx over 2. One half Kx squared is the formula for work. You could use d if you were, again, using displacement for how far the spring was stretched or compressed. But x is way more common, so I'll show you that. It looks really similar to the formula for kinetic energy, 1/2 mv squared, 1/2 kx squared. Not really related, but there you go, pretty close. It's going to be a short video, but it's still going to be pretty complex, so I'm probably going to split this into 2 days anyway. There's one last thing over here with you plus MGH, right? Right. Yes. So, having said that, now I'll do it. Again, the equations don't matter, the concept's important. Potential energy is when you do work and the object doesn't get kinetic energy, it gets some kind of stored idea that's stored potential to do work or stored potential energy. There's only two examples in mechanics: spring potential and gravitational potential. And those are the only two types we'll discuss until I feel like it. So that's good. So let's do a hypothetical problem. Let's say I'm in my classroom on the first floor, and I lift a bowling ball and I put it on my desk. Let's say the ball has mass Let's say the ball has mass. Let's put a bowling ball this way. I have no idea. 12, 6 kilograms. And let's say the height of my desk is 1 meter. And let's round G to 10. How much potential energy does my ball have on the desk? Easy calculation. Why do you even ask that? Of course you know how to do it. U equals mgh, mgh, 60 kilogram meters squared per second squared, also known as 60 joules. So this person is thinking U equals 60 joules. That's fine. But this is a weird idea. What if you were cutting class and hanging out in the cafeteria and watching the class with your X-ray vision? You guys are all super students, so maybe you have superpowers too, I don't know. And let's see, each floor of the school is 4 meters. Would you say the ball has 60 joules of energy? I look at the ball and I say, oh, its mass is 6 kilograms, its height is 1 meter, and G is 10. This bowling ball has 60 joules of potential energy. How much energy would someone in the cafeteria say the ball has? Would it be the same amount? Is that bad? Well, this person in the cafeteria would say, oh, U is mgh, and 6 kilograms, G 10 meters per second squared, H, not 1 meter. The ball will be 4 meters plus 1 meter, 5 meters above the person in the cafeteria. 300 joules. Who's right, the teacher or the student cutting class? I'm just kidding, you have enough of those. They're both right. Neither one's wrong. In this person's point of view, or relative to this person, the ball has 60 joules of potential energy. For this person in the cafeteria, relative to them, the ball has 300 joules. If they were a chemistry student on the second floor, the ball is negative 3 meters. They would say it has negative 180 joules. They're all right for their own frame of reference. So we don't really use this formula ever. We do this. That delta, it makes it work. It makes all the three people agree. 1, 2, 3. They all will get different values for you. But if I ask them this question, they'll all get the same answer. If I ask them, how much work did I do lifting the ball from the ground to the table? If I ask how much energy the ball has on top of the table, we get different answers. But if I ask how much energy I used lifting the ball 1 meter, delta H is 1 meter for everyone. So they all get the same answer. 60 joules. That's the work I did, and it's also the potential energy gained by the ball. Good job. Thanks. There's one more thing that I just want to talk about. Hopefully I can remember it, otherwise I'm look kind of silly. Potential energy, springs, physics. Maybe I can't remember. Maybe I'll tell you in class. Yeah, I guess so. I just had it in my mind, but I kind of lost it again.